right. One of the things that we developed yesterday was an arc length idea. Remember, we figured out that you could figure out an arc length in degrees if you just do the proportion.
Ms. Roberts, please contact the office. Ms. Roberts.
Times circumference. And then we found out when we changed that to radians, the formula simplified quite a bit and just became theta r. So if you were doing a question like question 3, and in the end they asked, what's the angle in degrees, we could use the green formula that we developed. Or you could do it in radians, and whatever answer you get converted in the end. And that's always fine as well. If the question's asking in radians, like this one says nearest tenth of a radian, we'll use the blue formula. But first of all, before we get into that, let's understand what this question is asking. Okay? We've got a space station traveling in a circular orbit around the Earth at a certain speed, 27,600 kilometers per hour. Its altitude is 400 kilometers. The radius of the Earth is 6,400. So what we're going to do is we're going to draw the Earth. Pretty nice little Earth thing you have in there. There we go. Does that look like the Earth? Okay. And then 400 kilometers on top of the radius. So the radius of the Earth is 6,400. And then another 400 is this space station. And space stations always make that sound. Okay, so there's our picture. It's traveling in a circular orbit around the Earth at a certain speed, 27,600 kilometers per hour. In 40 minutes, how far will this space station travel? Well, it's going to go along here a certain distance, and then we're going to have to find that certain angle. I don't know if I've drawn it long enough, but I just sort of got the basic idea. First of all, would you agree that 40 minutes, everything else in here is in hours? How do I change 40 minutes to hours? Divide by 60. So if I divide it by 60, 40 divided by 60, you could write it like that. That reduces to 2/3 of an hour. So in 2/3 of an hour, how far will that travel? We take 2/3 and multiply it by 27,600, and we get 18,400. Is that right? Someone can double check. So that is 18,400 kilometers. Okay, my scale doesn't look like it's very accurate at this point, because my 18,400 looks just a little bit more than my 400 kilometers. But that's okay. That's the nice thing about pre-calculus. You don't have to draw anything to scale. You just have to have the basic idea and then work from there. We want to find this angle theta. How much has it rotated? Can you see that we know the arc length? We know the radius all the way to the space station. And using our formula, this just becomes, with S equals theta r, we know that the arc length is 18,400. We don't know the angle, but we know the radius in kilometers is 6,800. The 6,400 plus 400. Dividing both sides. 2.7 and ask for the nearest tenth. So theta, look at, I remembered the squiggle. Theta is approximately 2.7 radians. So in reality, if I would have drawn this nicer, remember 3.14 radians would be halfway around. 2.7, I guess I'd estimate to be about there. That is a more accurate drawing of what happened. But if you drew the idea to begin with, since you don't know the answer, it's hard to draw it to scale, that would be fine what we started with. As long as you use blue for the planet and green for the land, they're going to check that. Okay. And in part B, to nearest 100 kilometers, what is the straight line distance between the initial and final positions of the space station? So now that we've drawn it accurately, we want to find out how far it is from here to here. Can you see that that makes a triangle? What do we know about that triangle? Well, it's not a right triangle, so we can't use SOHCAHTOA or a squared plus b squared equals c squared. What do we know? We know that these are both radiuses that are both 6,800. And in the last question, we found out that this angle theta right here was 2.7 radians, approximately. So now looking at labeling it completely, how did you solve for this last year? Every time you go 1 radian, you go 6,800. But now we're just looking for the straight line distance if you just traveled, instead of being in a circular orbit, if you just zipped straight across. And we would have to remember the Coase law to figure this out. So let's does this look familiar? And we can use the Coase law in radians, just like we can, at any time we got our calculator in radians, we can solve this using it in radians. What do we know? We want to find that opposite side, opposite the angle. I guess I should use a big A here, technically, because it's important that whatever angle you're talking about, the opposite side is on the other side of your equation. So for us, I labeled it with X in our question. We know that both of the other sides are 6,800. So we've got some big numbers. Here, and we can plug in Coase of 2.7. One of the things that we want to make sure that we're able to do with our calculators is not round any time early. Right? Remember, I found just type this in again. I found the 2.7 earlier by dividing. One of the buttons that you may learn to like to use on your calculator, right above the on button, is a store button. If you hit the store button, it allows you to store the answer you have as any letter that's here. The quickest one is hitting the X button right there. And now your calculator remembers that that's 2.7 with all the decimal places. So you don't have to retype it all. Depending on the version you have, sometimes you can select an answer from before by just going up and highlighting it and pushing enter. That's another thing that's helpful, but the store button works for all versions of the calculator. So now I can write in exactly what I see, 6,800. And I'd like you to do this all in one step. 6,800 minus 2 bracket 6,800 bracket bracket 6,800 bracket Coase. Now instead of typing in all those things and losing some decimal places, Since I stored it as x, I can just type x and the calculator will do that for me. Another thing that's also helpful is you can go second answer. This only works if the answer that you just found out the time before is the one that you want. If we do all of this, it figures out it's a very large number, and that's what's equal to x squared. So now I want to square root that answer.
Did Christian left? Please come to the office when it's convenient.
He's not here today.
Okay, thanks.
And we get 13,278. And to the nearest hundredth, that would be 13,300. Approximation sign. There are some more word problems in the homework. You might also want to read example 3 beside that one. It doesn't have as big of numbers because it's not dealing with planets and spaceships.